Lesson 11.5, Image Formation by Lenses. A lens is a thing made from transparent material, usually with a curved edge. A converging lens is thick in the middle, thin on the edge. It's called convex. Think like a magnifying glass. From the side, it looks like that. It's called a converging lens because parallel rays of light will come together or converge if they go through this lens to a focal point. You know, if you have a magnifying glass, you can burn paper with the sun if you put the paper at the focal point. A diverging lens is thin in the middle and thick at the edge, concave. If you're nearsighted, that would be the shape of your glasses. It's called diverging because parallel rays of light come in and hit the lens and separate apart. They diverge from each other. Power of a lens is 1 over f. F is the focal length, as you can see in the picture, and the power is measured in diopters, or capital D. So if you have glasses, your prescription is some amount of diopters. The focal length, f, is the distance from the lens to the point where all the rays of light converge. We will solve some problems or see how they work by using what are called ray diagrams. Ray 1, we're going to draw 3 rays of light. Ray 1 is parallel to the principal axis, and then it bends through F, the focal point. Ray 2 goes through the focal point, hits the lens, and then bends parallel to the principal axis. And ray 3 goes through the center of the lens, and because it's going through the center, it does not bend. For example, here's what we call the principal axis. That's my lens. It is right centered on the principal axis. The principal axis goes to the center of the lens. Those are my focal points. You have one on each side of the lens. And then I have a point that's twice the distance of the focal point. And I have some object. I'm going to use an arrow. Now, technically, light is coming from all points on the object. We are just going to use the tip of the object. Ray 1 goes from the tip of the object to the lens parallel to the principal axis. After it goes through the lens, it bends through the focal point. So it bends through there. So that's ray 1. Goes parallel, hits the lens, and bends through F. Ray 2 starts at the top of the object, goes through the focal point, and hits the lens. After it hits the lens, it bends parallel to the principal axis. So this is ray 1, this is ray 2, this is ray 1, this is ray 2. Ray 3 just goes to the center of the lens and does not bend. So it starts at the top of the object, goes to the center of the lens, and doesn't bend. So this is ray 3. Notice over on the right-hand side, all 3 rays intersect at one point. That will be the tip of the image. So the image will be right there. So what do you notice about this image? Well, it is, if the object is beyond 2f from the lens, the image is inverted, meaning it's upside down. It is real, the rays really cross at that point. It is smaller, and it is between f and 2f. So if you drew everything carefully to scale, you could actually measure exactly where the image would be. Let's try a different one. This time, let's put the object between 2f and f. So I have the principal axis, our lens, f, and 2f. Make sure you measure carefully. You can't guess. You must use a ruler when doing these, or else it is all messed up. Alright, so my object is there between 2f and f. Ray 1, what did ray 1 do? That's right, it goes from the top of the object, parallel, and then hits the lens. And then it refracts and goes through f. This is ray 1. Alright, what did ray 2 do? Ray 2 started at the object and goes through f, that's right, and then bends parallel to the principal axis. So this is ray 2. And ray 3, what did that do? That's right, it went through the center of the lens, did not bend at all. This is ray 3. So where's our image going to be? Over there. So when the object is between 2f and f, the image is real. The rays really cross there. It is inverted and larger. It is also located beyond 2f from the lens. Let's try one more. Let's put the object between f and the lens. There's my lens, there's my f, there's my two f's. Again, when you draw all these, make sure you use a ruler to draw it correctly. Our object, I'm going to make it really little. It's between f and the lens. All right, ray 1, what does ray 1 do? That's right, it goes parallel, and then it bends through f. This is ray 1. Ray 2 goes through f. The only way to make it go through f is if we line up f and the top of the object, and it goes up like that. So this is 2. And it bends parallel. It's 2. Are you seeing a problem? Ray 3 goes through the center and doesn't bend. So where's the image? That's a problem, isn't it? They don't meet. So what we'll do is we'll trace our refracted rays backwards. So here is ray 2 going backwards. Here is ray 3 going backwards. Here is ray 1 going backwards. And now, notice they all meet at a single point. Our image is back there. But do these rays really meet at that point? No. That means that it is virtual, upright, between 2f and f on the same side with the object. As long as you're using only one lens, if it's real image, it'll be inverted. If it's a virtual image, it'll be upright. For a diverging lens now, try this again. Ray 1, it's now going opposite, it's diverging. So now ray 1 bends away from the axis so that it looks like it came from f. Ray 2 starts by aiming at the far f instead of the one on its side. And ray 3 is the same. There's a principal axis. Our diverging lens, remember it's thin in the middle, thick at the edges. Our focal points, and twice our focal points. Put some object. All right, ray 1 is now bending away from the axis. So we start with it going parallel to the axis. That's ray 1. Hits, and it bends away as if it was coming from that first focal point. Ray 2 aims at the focal point on the opposite side and then bends parallel. This is diverging, so we're going to follow it back. So that was ray 2. Ray 3 goes to the center as before. So it looks like our image is right there. It is virtual, upright, and smaller between F and the lens. If you're nearsighted, you can see this by taking your glasses and holding them a long way away. You see that your image is smaller. Conveniently, there's also an equation that does all this. The thin lens equation. 1 over f equals 1 over object distance plus 1 over image distance. If it's a converging lens, the focal length is positive, and DO and DI are positive if they are real. We also have a magnification equation, which gives us our heights. Magnification is our image height over our object height, which equals our negative image distance over object distance. For diverging lenses, for both of these, our focal length is negative. And if something is virtual, such as a image distance, a virtual image, would be negative. So let's use our lens reasoning strategy. Examine the situation to determine that image formation by lenses is involved. I mean, if it's not a lens, this isn't going to work. 2. Determine whether ray tracing, the thin lens equation, or both are to be used. A sketch might be useful even if ray tracing is not specifically required. Identify what needs to be determined in the problem, so you need to know the unknowns. 4. Make a list of what is given or what can be known from the problem. That's helpful to determine whether the situation is a case 1, 2, or 3 if they are converging lenses. The first one we did was case 1, the second one we did was case 2, the third one we did was case 3. If it's ray tracing, step 5, use the rules. Step 6, most quantitative problems require the use of the thin lens equation. These are solved in the usual manner as before by plugging in knowns, solving for the unknowns. And step 7, make sure it's reasonable. Does it make sense? Does it fit the type of image from our examples that we just did with the ray tracing? So a child is playing with a pair of glasses with diverging lenses. The focal length is 20 centimeters from the lens and his eye is 5 centimeters from the lens. A parent looks at the child's eye in the lens. If the eye is the object, where is the image located? Well, we could use ray tracing or we could use the thin lens equation. That might be easier. It's diverging, so that means our focal length is negative 20 centimeters. As long as we have all the same units, it doesn't matter what unit we use. So I'm going to use centimeters. 1 over f equals 1 over object distance. This is the object is his eye. That's 5 centimeters from the lens. It's a real object. Plus 1 over image distance. Subtract the 1 over 5 centimeters. Get a common denominator and combine those. And you have 1 over di equals negative 0.25. Take a reciprocal and you have di being negative 4 centimeters. Since it's negative, that tells you it is virtual and on the same side as the object. If its eye is really 3 centimeters across, how big does it appear? Well, that sounds like size, so we should use our magnification equation. Well, we know it's really 3 centimeters, so that is the object height. We know the image distance from the first part, and we know the object distance from the problem. So we can fill those in. HO was 3, DI was -4, DO was 5. Again, as long as the units are all the same, this works. Multiply both sides by 3 centimeters, and you get 2.4 centimeters for the image height, which means it's smaller. If we go back and check diverging lenses, the images were virtual and smaller. So it makes sense. Form an image in your mind of doing well. That will help you do well. Have a good day.